The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
So I'd like to introduce our very next and last speaker for the day. Megar Marceau is a licensed professional engineer and building science consultant at Morrison Hershfield. For more than 12 years, he has provided consulting services in the fields of building science, life cycle assessment, and sustainability. He has extensive experience in building envelope systems, whole building energy simulation, and life cycle assessment. Megar has authored and co-authored dozens of publications on the subjects of sustainability, life cycle assessment, and energy use in commercial and residential buildings. He received his bachelor's degree of science and engineering from the University of New Brunswick and a master's degree in applied science from Concordia University, and has an applied mathematics degree from DePaul University. He is a member of ASHRAE, the Construction Specification Institute, and he is a life cycle assessment certified professional and a lead accredited professional. Please help me welcome Megar Marceau.
Thank you very much. Well, thanks everyone for coming. I'm really glad to be here. So I'm going to try and take a step back and kind of look at the information that you've seen so far from a higher perspective. So we've talked a little bit about thermal mass, and we didn't really talk about what is thermal mass, but it's anything that has the ability to store heat, hold on to it, and release it later on at a later time more gradually, such as earth, concrete, masonry, and water. We didn't really talk about where we use the thermal mass to reduce energy use, but we're really going to talk about using it in the building envelope, so that's the skin of the building, and in the building structure itself, like the interstory floors. And as we heard from Jeff this morning, increasingly we'll start to see it being used as part of the heating and ventilation system, like through chilled slabs and heated slabs. So one of the big questions that I have in my mind about this whole seminar is, number one, why are you here? What information are you trying to learn from these presentations that you can take back to your clients and to your customers? But also, why are we talking about saving energy? There's a whole bunch of different reasons why you may want to save energy, whether it's to meet code, whether it's to reduce your energy use, whether it's to reduce your carbon footprint, whatever that happens to be. But the information that I'm going to talk about really centers around getting buildings down to net zero. So that's buildings that produce at least as much energy as they use. So their net energy consumption is zero. We're not going to talk about carbon neutral buildings or thermal comfort buildings, but those are other reasons why you'd want to use a strategy like thermal mass to reduce your overall energy use. And then the next big question I have is, who's the decision maker? So who is the person in the whole design and construction process that determines whether or not the building is going to have thermal mass in it, whether it's the walls or the floor? And it could be any of these players here, the architect, the mechanical engineer, the structural engineer, the building envelope engineer, the owner even, or some consultants who work on lighting and acoustics who might have some input on using thermal mass inside the building. But I really think it's the architect who decides. If they're passionate enough about a material or a process or something, they'll make it happen in the building. So a lot of sort of interesting energy features in buildings are there because the architect has a passion for it, and they're the champion for it. And I don't really see too many architects having a passion for thermal mass. So I think that may be one reason why we're not seeing it being used in more buildings. But I think there's other reasons, and I'll get into those in the presentation. And then, of course, we talk a little bit about how to use thermal mass in the building as a strategy to reduce overall energy use. We've got information from traditional forms of architecture that show us that thermal mass works really well and makes the building more comfortable. Classic example is Adobe-style architecture. We've got lots of experience with passive solar houses, decades of experience now, and hundreds of publications that tell architects exactly what the building needs to look like, what materials need to be used, what form it needs to have to reduce overall energy use. But what we're really lacking is information in the commercial building sector. And I think that's because energy use in commercial buildings is so complex. There are so many loads on the building that are time and weather dependent, and all the systems in the building that control heating and cooling are also very complex and have to respond to the weather, have to respond to people and crazy things they do in buildings. So energy use in buildings, in commercial buildings, is a very complex topic. And what we're trying to do in this presentation is to simplify it down to just a few parameters, right, so we can talk about it intelligently. But that's pretty difficult, as you'll see. So just to kind of give you a bigger perspective about the design and construction in buildings, this is the traditional design phases for architecture, starting at concept phase or pre-design, where the architect meets with the owner to determine the owner's project requirements, and they also do some background research on what the site has in terms of what the site resources are, so what the prevailing winds are there environmental considerations, like is it a wetlands area, what are the local zoning requirements for buildings. Then they move into the schematic design phase, where they take this information and come up with some general ideas of what the building will look like to meet the owner's project requirements. And that'll typically be a floor plan, a site plan, a couple of building elevations, and some building cross-sections. But nothing more detailed than that, typically. Then, during the design development, they take the next step and they choose one of those schematic designs and further develop the details. Then, during construction documents, they take those design ideas and produce a set of construction documents that someone can actually build and bid on. Then there's construction and occupancy. So one of the questions I have, does anyone know when energy modeling happens in this design and construction phase? Do you think it happens at the beginning during the concept phase? Do you think it happens? Yeah. Yeah, so usually energy modeling happens around design development. And by that point, a lot of the building form and fabric has already been decided and kind of set in stone, if you will. So then the energy modeler is left with trying to make the best they can of a not-so-good situation. So what I think we need to see as an industry in terms of making buildings more energy efficient and using thermal mass more intelligently is to front-end load this process and do a lot more work earlier on in the pre-design phase of building design and construction. So here's an example of what this might look like. And there's a lot of information here, and I'm going to go through a few of the steps, not all of them. But basically what it is an energy modeling process to walk architects and mechanical engineers through a step-by-step process from pre-design all the way down to post-occupancy so that they can use the energy modeling tools to really design low-energy buildings based on real measured data. And so the first thing you need to do is consider the climate, because the climate determines what free resources are available for you to heat and cool your building, and it determines what are the loads that are going to be on your building, the heating and cooling loads. After you've done the climate analysis, then you can set some goals for your building that are realistic for that climate. Then, this is all in pre-design, you create a pre-design baseline model. And that's a very simple computer representation of the building before anything's been drawn. So it's just a generic model of your building. And using this generic model, you can do a lot of what-if scenarios. What if I double the floor thickness? What if I decrease the amount of mass in the wall by half? What if I put an R value of 40 in the walls versus the code required minimum? And because this is a pre-designed baseline, you can do this really quickly. The model's not very complex. And you can get a lot of really useful information that you can make design decisions on really early on. So that by the time you get into design development, when the building form is already taking shape and it's kind of fixed, you can kind of dispense with all those what-if questions. You already know what the ideal monothermal mass is. You already know what the ideal R value is. You already know what kind of HVAC system is appropriate for that climate for that building. And so you can kind of focus on, the architect can focus on the design of the building and making sure it all comes together. So here's kind of an example of a climate analysis. This is just a psychrometric chart where we plotted all the temperature and humidity data for a typical year in a specific climate. And this is Bellevue, Washington, where I work. And overlaid on top, and so that's all those blue and white squares. And the blue squares show you kind of the relative number of those hours that occur in that year. So it kind of shows you that, as you would expect in Washington, on the West Coast, it's pretty much cold and wet most of the time. So cold temperatures, 10, 15 degrees, and very high humidities. But using a software tool called Ecotect, you can overlay on top of that the impact of different design strategies that can take those outdoor temperature hours and expand the number of hours where you'd be comfortable inside a building just with the existing weather conditions that are outdoors. So on top of that chart are plotted things like passive solar heating, thermal mass effects, exposed mass, and night purge ventilation. And then you can look at the strategies that result in the greatest number of hours where you don't need to provide any mechanical heating or cooling inside your building. So just using the free resources of the climate where you are. And for this particular building, in this particular climate, the two strategies that make the most sense are using thermal mass in the building structure to absorb excess heat, and using night purge ventilation, where during the daytime the mass absorbs the heat of the outdoor temperature in the sun, and at nighttime you bring in ventilation to cool the mass down so that the next day the mass is cold and is ready to absorb excess heat during the day. And it's a way of offsetting air conditioning loads. And I'll show you a specific example of where this was done in a climate that's similar to Seattle's. So the baseline model is very simple. It's basically a shoebox model. I'm not going to go into this, but basically a rectangle. The only important thing to get right in this baseline model is you need to know what the floor area is of the actual building. So you get that from the architect. The height and number of floors, and occupancy schedules for people and lights and equipment. Because those occupancy schedules determine when people come into the building, when you need heating and cooling, when you're going to use lights which generate heat, which need to be taken away by the cooling system. And then you can analyze the results using what's called the Parametric Study. And what the Parametric Study is, I'll show you a picture of it, and then I'll explain what it is. What you basically do is you go through your building baseline model, and you look at all the loads on your building, and you eliminate those loads in the model one by one to see what effect they have on the building. So for example, you might look at eliminating the opaque losses. So what this does is it tells you, or you tell the model, I'm not going to have any heat transfer to my building envelope. And this is a way of looking at what's the most energy savings I can get out of a building if I have the best thermal performance possible. So like, an R100 wall. And so you plug that into your baseline model, you run the model, and it turns out if your building envelope is perfect, it doesn't let in any heat through the opaque portions, you can save 11% over a baseline building. And the baseline building is actually quite arbitrary. It's whatever you choose for your particular project. In this case, we use ASHRAE 90.1, the energy standard for the baseline. Then you do that for every load, for every envelope component of your building to look at what's the most energy savings I can bring out of these individual systems. So you do the same thing for glass conduction losses to see what's the effect of having really good insulating glass versus single pane. Same thing for solar gain, infiltration, and then all envelope parameters together. And that gives you an idea really early on where to focus your design efforts to make the building more energy efficient. So in this particular case, most of the energy savings come from opaque gains and losses and infiltration. So that tells the architect, before they start to design anything, where they should focus their design effort to make the building more energy efficient. That tells them you need to focus on reducing thermal bridging, and you need to focus on making the building envelope more airtight. For this particular case, the glass conduction is only 6%, which isn't that much, and so that tells the architect right away, you don't need to do a whole bunch of studies on what kind of glazing to use. Code minimum for this particular building is good enough. Then you do the same thing for the loads in the building, lights, people, plug appliances, ventilation. And this tells you how sensitive your model is to your assumptions about how the building is going to be used. And as we'll see in a few slides, those assumptions about how the building is going to be used are usually wrong in energy modeling. And buildings use a lot more energy than modeling predicts. So one of the needs that we have as an industry, both in using thermal mass but also in modeling energy, is to get better predictions of actual energy use using real measured data to calibrate and check our models. So here's just a simple example of using a parametric analysis on thermal mass. I can give you a reference to this paper if you're interested. It basically shows 3 different cities for a commercial building, the relative energy savings you get by including thermal mass in the envelope and in the structure. So the low mass building uses the highest energy and has the highest energy cost for all 3 of these cities. Using mass in the structure and in the envelope reduces that energy use and energy cost, and then combining kind of the best envelope strategies, minimizing thermal bridging, minimizing the size of windows, because you don't need windows to be very big to get natural daylighting. 20% is kind of a rule of thumb. And improving the Scholl heat gain coefficient of the windows can go a big way, combined with thermal mass, to reducing energy use and cost overall for these types of buildings. I'll skip this just to save some time. So then the next step in the whole energy modeling process is to take what you've learned in the pre-design, create some realistic goals for that project in terms of reducing energy use, and then do a detailed study on those potential energy saving measures. So I'm just going to go through the schematic design baseline model kind of step by step, only to make a point about the heating, ventilation, air conditioning system design. So in a schematic design, and again, this is before you've designed very much of the building. There's very few drawings, so very little is written in stone. So in schematic design, you take the diagrammatic building plans, incorporate building envelope and thermal mass design strategies to reduce loads on energy-using systems. That's kind of like the second stage. Develop a site plan, select the building systems and efficiency levels, develop building plans, sections and details, design review to verify the project meets the original goals. Now at this point is when you calculate the building's HVAC loads. What typically happens is the building's HVAC loads are calculated before any design decisions are made, on reducing the loads in the first place. So then the next step is to match the capacity of the HVAC system to those reduced loads. Instead of doing it the other way around, which is what we've been used to doing, is first designing the system based on assumed loads and then trying to reduce the loads after the system has been designed. And then finally perform a final coordination and integration of the architecture, mechanical, and electrical systems in the energy model. Develop specifications, and then finally, as part of schematic design, is to develop a set of commissioning standards or procedures. And the purpose of doing this is to make sure that what you've designed is actually what you get when you build the building. So the owner just determines how they're going to demonstrate that what they want in their owner's project requirements are actually being delivered at the end of the construction process. And I'm going to skip through a bunch of these for the sake of time. So here's some information that's produced by the New Buildings Institute in Seattle. And what they've done is they've gone out and they've measured a lot of buildings. And they've actually looked at how buildings really use energy use. And then they've made some computer models to predict how those same buildings would work in other climates using that same measured data. So the models are calibrated to actual conditions, actual real-world conditions. So what they did for this example, this is for Seattle, and we have this information for 8 cities across the U.S. It's only for one building type. It's only for commercial office buildings, kind of medium size. But there's a need for doing this for other building types as well. So what we have here, the 0% is kind of average construction. So they figured out for commercial buildings in Seattle, what's typical average real-world construction? R6, R7 walls, economizer on the HVAC system, you know, kind of basic stuff. Then they looked at what's typically used in a high-performance building in Seattle, and how does that affect energy use? So that's what they plotted on the green bars below the 0% line. And then they looked at what are some of the crazy things that actually happen in the real world that make energy use increase. So things like excessive thermal bridging, or the wrong kind of glass was installed that doesn't have a solar heat gain coefficient that was specified, or the building's economizer system is rusted shut and doesn't work. And that's what they plotted on the upper scale to kind of show what's the additional energy the building could use if things go wrong. So what they showed right here is, you know, air tightness, number one, for buildings that are designed to be airtight, compared to a baseline building, that reduces energy use by about 4%. So not very much. Buildings that are pretty leaky, they can use more than 5% more energy than kind of the standard building type. Going all the way over to mass, buildings that are a lightweight building, they don't have any thermal mass in them, can use up to 7 or 8% more energy than a typical building in Seattle. And by incorporating thermal mass into the structure of the building, and this just looked at thermal mass in the floors of the building, energy use can, you can save up to about 4 to 5% energy over a typical weather year. Okay, so the first part of this graph on the left-hand side is the same charts you've just seen. And this is all envelope stuff. Then the next few charts are lighting. Then there's HVAC stuff. Then there's operation. Look at HVAC system. The choice of the HVAC system is, in terms of design, has the largest impact on any other choice. Whether it's thermal mass or R value or thermal bridging. So in terms of reducing buildings' energy use, thermal mass is important, but the HVAC system choice is very important. And then look at the thermostat set point. That has the highest impact on buildings' energy use. So a lot of things that architects and engineers can't even control, like thermostat set points, how occupants use the building, how they run their data centers, those have the biggest impact on energy use in buildings. That's why it's so important that when we do our energy modeling, that we go back and get real data to update our energy models so that when we make design decisions based on a model, we're actually reflecting real-world conditions. It also tells us the importance of making sure that high-performance buildings are being operated the way they're intended. You know, a classic example is buildings with natural ventilation, where the building has automatic windows that close when outdoor conditions aren't right for ventilation, but sometimes the occupants will open the window anyway. And so that kind of sabotages the natural ventilation strategy. Or using night purge ventilation when you have thermal mass. The idea behind that is at nighttime when the temperatures come down to bring in cold outdoor air to discharge all that heat in the mass so that the next day when the sun comes up and things start to warm up, the mass in your building is nice and cold to absorb that excess heat. Well, If the operations staff finds it too inconvenient to keep maintaining windows that open and close automatically, they may just not maintain them, and then natural ventilation no longer works. And so this strategy that's been designed to make the building use less energy is being sort of sabotaged by the operations staff because it's just too much work to maintain the systems. So here's an example of a building. It's actually in Melbourne, Australia, and it's a building that uses a whole bunch of different strategies to reduce energy use. And I want to show you this one because they use interior mass inside the office space in the ceilings to offset their cooling load. And what I like about this building is they've published a lot of information on the actual use of the building. And this graph is really busy, but all I want you to focus on is the pink line, which basically is the temperature inside the space. And so from 12 a.m. to 6 a.m., the temperature inside the space is getting colder and colder and colder. That's because they have night ventilation, bringing in cold air from outdoors. Then from 6 a.m., the space starts to get warmer and warmer and warmer, and that's because the sun's coming up, people are coming into the building. And for this particular building, from 6 a.m. until 12 p.m., the thermal mass in the ceiling is enough to offset all the cooling load requirements. So they don't have to run their air conditioner until after lunchtime in this particular building. And in this building, they've got some other strategies that are used to move heat around using phase change materials to offset the rest of the cooling energy. So in this particular building, this is a real life building, this is real measured data. Thermal mass isn't producing all the cooling, but it's offsetting a significant part of the cooling. And this building has one of the lowest energy use intensities in Australia. Now here's another building. It uses a lot of the same strategies. It's in Seattle. Some of the same energy modelers worked on this building as the one in Florida, in Australia. But this one doesn't use thermal mass in the ceiling. It's the same kind of office, it's the same kind of climate, and why don't we use thermal mass in the ceiling? Thank you. The answer is the structural engineer didn't want to have any more mass in the building because Seattle's in a seismic area. And to meet his seismic design, he wanted to have as light a weight of building as possible. So this kind of goes to show there are a lot of interrelated factors to using thermal mass. It's not just a matter of putting it in the building. There are a lot of other considerations that we as energy modelers often don't think about, like seismic structural issues. So then to kind of summarize this section, the overall strategy to reducing energy use in buildings should always start with load reduction. So before you do any design, before you do any mechanical sizing, it's the number one, reduce the loads on the building. Number two, use passive strategies to make up for that additional load, like daylighting, natural ventilation, thermal mass. Number three, use the most efficient mechanical systems you can afford. Number four, use energy recovery. Number five, use renewable energy for the remaining energy that you have. And number three, where renewable is not practical, buy offsets. And so this is kind of a strategy that's used in a lot of high performance, low energy buildings to get them down to that net zero target. So just a few things that, like you may have heard these things before, but these things always work at reducing energy loads in buildings, regardless of where the buildings are in the US. Minimize glazing on the east-west sides of the building. That always reduces energy loads. If you could have no windows on the east-west facade, that would be ideal. Unfortunately, in some places like Seattle, all the views are to the west or to the east. And so building owners want to have all their glass on the west and the east. That building that I showed you the drawing of, that was one of their issues, is they wanted the views to the west of the mountains. And so they put a lot of glass on the west. But they knew up front that this would cause them to use more energy than they would if they had put all the windows in the north and the south. But at least they had the information to make an intelligent design decision. Minimize solar gains with shading during peak cooling periods. Optimize the R value for the climate and building occupancy. Eliminate thermal bridges. Use thermal mass. It works in most climates. Maximize southern exposure, and orient the building with a long axis east-west. These are all strategies to use the free energy of the sun and the climate to reduce energy use and use prevailing winds for ventilation. So the last part about this presentation is going to kind of talk about some of the needs that I see as an energy modeler when it comes to thermal mass. So I know that thermal mass can save energy. And I know that integrated design and post-occupancy data shows that thermal mass saves energy. But a lot of buildings don't use thermal mass to save energy. And why is that? I think part of the reason is because energy modeling is not very accurate because of our inputs. And we assign to energy modeling an unrealistically high baseline model that we make our comparisons to. So typically the baseline model is the energy code, but how many buildings in the real world are built and perform the way the energy code says they're supposed to? The energy code says, in Seattle, for example, you need R19 insulation in the stud walls, and then about R8 continuous insulation outside the stud walls. And I've reviewed other energy modelers' models, and they've modeled the R value of those walls as R20. Well, it's not R20. There's thermal bridging at the slab edges, around the windows, at the roof line. There's all kinds of issues. You're lucky to maybe get R5. So the benchmark building is modeled as R20, because that's what code tells you to do. And then the architect's scratching their head and they're thinking, how can I get better than R20? I'll try R25. And energy modeling says, doesn't have any impact. You don't save much more energy. Well, it's because the benchmark that you're comparing to, it's unrealistically high. It's already a high-performance building, in my opinion. So we live in a 3D world. Heat loss in the third dimension is real. It's often not it's rarely accounted for in energy codes, and it's almost never accounted for in thermal modeling. And the impact of heat loss in 3D can drastically reduce your R value. And I'm only showing you this information because I think kind of in the thermal mass world, we need something similar like this study to show us a simple way of dealing with thermal mass in the building envelope and in the building structure. So this study is from ASHRAE that my firm worked on over the past couple of years, and we looked at modeling heat loss in 3 dimensions for typical building envelope details in the commercial building sector. In the old days, very recently we'd use 2D modeling, even hand calculations, even laboratory measurements to calculate or measure the building's R value. Well, that works really well when heat loss is 2-dimensional, but it's not, it's 3-dimensional. So the purpose of this project was to look at typical details and calculate the effective R value of those details, if you will, and come up with a way that makes it really easy for energy modelers to put this information together and get the input for their energy models of what the building envelope R value really is. I won't go into the details, but here's some typical details we looked at. Cladding attached through exterior insulation with metal girts, window openings, curtain wall openings, precast concrete, cast-in-place concrete at all the transitions. And we kind of had this breakthrough moment where we realized to calculate heat loss through a complicated 3-dimensional detail, like this slab edge, for example, that heat loss is equal to the heat loss through the wall minus the heat loss through that slab edge and the wall. So we can model both those two conditions on the left really easily with the computer modeling. And subtracting the two gives you the heat loss due to the slab. And so now with this result, I can take the heat loss due to the slab, divide it by the length of the slab, and find out how much heat loss I have in that whole building because of the slab. And if I know I've got 20 stories and they all have slabs like this, I can figure out the heat loss through all the slab edges and divide by the area, and I can get the effective R value because of the slab edge. It's called linear transmittance. And I think what we're going to see is, I hope what we see, is in the next few years, we're going to stop talking about R values and U factors, and we're going to start talking about heat loss. How much heat loss is there through the envelope? So I showed you like a slab edge condition. You can do the same thing for a point load, like metal supports that penetrate the building envelope to support a canopy. That's just the equation. Let's get through that. So the outcome of this work was a series of tables. On the right-hand side, so the left-hand side shows you the physical materials in detail, and on the right-hand side shows you the model performance. And using this table right there, you can really easily read off, okay, I've got R13 bad insulations installed in my wall, I've got R10 continuous insulation, my effective R value is R16.3. This is really easy to use. And within a few minutes, you can calculate the building's overall R value way more accurately than we've been doing it before. If you were going to do it using 2D modeling, it would take several days to do that. So the purpose of showing you all this is just to show you that we've come across this new way of getting information that's a lot easier, that makes modeling much more accurate. So we're actually going to do it now. And I think we need to do something similar for thermal mass, to take all this complex information, distill it down into some form that's really easy for designers and energy modelers to use, so that when they're telling the architect thermal mass does or does not save energy, it's based on kind of real-world measured data. And I'm going to skip to the end of the presentation. Thank you very much for your time. Do you have any questions?
Thank you. Any questions for any of our speakers? This is a good time to do it. Please step up to the microphone.
Hi, my name is Ben Shapa. I had a quick question. You made a comparison, or you said that building design, one in Australia versus one in Seattle, and you said the thermal, the mass was not used in the sealants for structural reasons. How did the energy performance of the two buildings compare? Was there a significant loss, gain, or how did it compare?
Oh, that's a great question. We don't know yet because the building in Seattle hasn't been built. It's under construction right now. So in a year and a half, I'll have the answer. I can tell you what the modeled energy savings are, but that's not really useful until you actually calibrate it with how the building's being run. Because, I mean, I'm an energy modeler and I use it all the time, but the number you get out of energy modeling is often not close to what's the real energy use in the building.
Yeah, you say not close, not far off.
It can be 100% off, it can be 5% off, it can be right on. It depends how good your energy modeler is and how good the information is they put in. The classic garbage in, garbage out. You know that one?
What is this data center?
Oh, that's data center. So some buildings weren't intended to have a data center in them during the design phase, and then during building occupancy, the owner put a data center in there.
And so all the computer servers and everything,
all
that tremendous cooling.
Yeah, it's all the computers and servers and stuff. Not computers, it's servers.